So yes, welcome to the next session, and the first talk is we are still in the area of SubsetSum, and the first talk is by Manuel Klein on finite complexity and the Frobenius problem.
Yeah, thanks a lot for having me on. Yeah, I would have liked to be there in person, but yeah, that's how it is. Still, I'm happy to join in online here. So I hope you're up for even more SubsetSum. SubsetSum.
But how are you? Are you okay? Kim, are you fine? You feel good?
I'm good. I already was talking a bit, like I'm still a bit exhausted, like it drags on for a bit longer than I thought. But it's fine, so we'll see if I manage through the whole talk. It will be fine. So yeah, SubsetSum Unbounded also kind of sounds like the sequel talk, right? Oh, change, okay. Yeah, so essentially the reason why I actually was interested in SubsetSum, it's just because it's like the easiest integer program that you can think of. Like you have an integer program in standard form, having just a single constraint. And it was surprising to me that I actually didn't understand anything about, I did not understand like completely everything about that already very easy integer program. So essentially we are given item sizes. So we call the A0 to AN the item sizes. And we assume that they are sorted. So A0 is the smallest item size, AN is the largest item size, and we call the right-hand side the target vector T. So then the unbounded SubsetSum problem is simply to decide whether the integer program is feasible. So in contrast to the classical SubsetSum problem, which Carl talked a lot about, is now we may choose arbitrary multiples of each item size. That's the only difference. And that actually makes the problem easier. So the way kind of I think about the problem is the following. Like you think of a line of numbers, 1, 2, 3, 4, and so on. By the way, can you see my mouse pointer?
Yes.
And we make a cross each time we can hit the target value. So we make a cross each time the IP is feasible for the target value. So in that, we also say then T is a feasible target value in that context. So for example, here we have item sizes 5, 7, and 9. Of course, then we make crosses at 5, 7, and 9. And then, of course, at all multiples of 5. And one important property to notice is if you look at the intervals, like 0 to 4 and 5 to 9, then the crosses here in the interval, they are always a subset of the next crosses. Simply because you can always add A0, the smallest item size, to maintain the cross, of course. And then a very interesting thing happens. At some point, like there's a threshold, where every target value starts to be feasible. And therefore, like there has to be a largest target value that is not feasible, and that is called the Frobenius number. So in our case, this is the number 13 here. And after 13, every target value will be feasible. That is actually very easy to see. But you need to assume one thing. You need to assume, of course, that the GCD of the item sizes is 1. Otherwise, of course, that would not be possible. And the problem of computing the Frobenius number is called the Frobenius problem. Yeah, but there are actually plenty of other names in the literature, like it's also called the coin problem. And then there's also a subvariant of the problem, which is called the McChicken problem. So there are kind of very different names in the literature. And I would say in general, there are two different communities involved with the problems. Like for the SubsetSum problem, of course, like there's this SubsetSum community, which studies a lot convolution and stuff. But there's also a very large community behind the Frobenius problem, which is mostly mathematics people, I would say. And there's tons of literature about the Frobenius problem. Like for instance, I can recommend the book of Alphonsine. It covers 400 sources of papers, which only study the Frobenius problem. Like for instance, they study bounds on the Frobenius numbers, upper bounds and lower bounds, and different generalizations. So there's really plenty to look at. And yeah, but my impression was so far that people are not really talking to each other. And the message of the talk is, I think, if you want to solve either of the problems, you should be aware of like this this dichotomy that happens. Okay, so far I think we haven't been that really. So in a sense, what we did so far in integer programming was the following: if your right-hand side is large, then we use proximity. So we compute a fractional solution that is close and essentially reduce the right-hand side. But in our case, that is not necessarily actually a good idea, because we actually make an easy problem hard. The issue is we can easily decide if we are larger than the Frobenius number, the problem, or let's say we are larger than delta square, an squared, then we can easily compute a solution by using the Euclidean, extended Euclidean algorithm. So the problem is not even NP-complete anymore. So it's not a good idea to use actually proximity here. So here I want to mention some technique on how to make use of this dichotomy that actually happens. And how, kind of, I want you to understand that these problems are intrinsically related to each other. Okay, and then there's a generalization, a very natural generalization of both of the problems, which is to compute the so-called residue table. So the residue table is simply so we consider residue classes modulo A0. And for each residue class, we are interested in the minimum target value such that T is feasible. So for example, for residue class 1, we just want to find the first cross. Okay, so 1 has no cross, 6 has no cross, 11 has no cross, but 16 has a cross. So we put in 16 in the entry 1 of the residue table. Same with 2, right? First cross, 2 is 7 here, and so on. So in this sense, the residue table is simply a data structure that solves the SubsetSum problem for arbitrary target values in constant time. So if you have computed the residue table, you can decide very easily on the feasibility of a target value, right? Because the target value T is feasible if and only if T is greater or equal than the entry in the respective residue table. And also we can compute the Frobenius number simply by taking the maximum entry in the residue table. We know that entry is feasible and representable, but the entry minus A0 is not. Okay, so this has to be the largest target value that is not representable. Okay, so in our case, you see the largest entry was 18, minus 5, this is just 13. So any questions so far? Please interrupt me, of course, anytime. Okay, so what do we know so far on the problem? So So one, I think, algorithm that is not very well known is the algorithm by Bücker and Liptak. This one computes the residue table in times n, so number of items, times A0. And that is actually a very elegant algorithm. It uses a kind of a dynamic program using round-robin procedure. And you can understand it in 10 minutes. It's very elegant and yet clever. There were algorithms before to solve the problem that were less efficient. Essentially, they were computing a shortest path in the Cayley graph. And yes, we were listening to Carl, like there's also an algorithm by Carl with a running time of t log t. And the algorithm by Janssen and Rohweider also solves the problem in nearly linear time, depending on the largest item size, an, in quasi-linear time. And there's also this known lower bound. I think Carl was talking about it. I will also come to talk about it later. And so, but essentially, the running time cannot be improved to a sublinear dependency on t or an. So this is what we know about the problem so far. Okay, so let's think a bit about the residue table. What properties does it actually have? The residue table has to fulfill some subadditivity properties. So there must not be indices I and j such that ai plus aj is less than the entry of ai plus j modulo a0. Why? Because then we would have a better solution to that residue class, right? Because we could add up the solution, the target value that we can represent here, plus the target value that we can represent here, and would obtain a better solution. So in that sense, the residue table always fulfills this subadditivity property. And here we know by the paper of Sügen and others that already checking this property is equivalent to min plus convolution. Yeah, so here I'm actually considering the cyclic variant of the min plus convolution. So essentially we allow for some kind of wraparound. So if the indices exceed n, then we compute them modulo n. Okay, but it's easy to see that the problems are equally subquadratically equivalent. So if you can solve the other problem, the one problem, you can solve the other problem. And yeah, Carl was also talking about it. There's this conjecture that min plus convolution cannot be computed in subquadratic time. But what we're going to prove is actually we show equivalence of our problems to the min plus convolution. So even if you do not believe in this conjecture, it doesn't really matter. Because if you find a better algorithm for min plus convolution, then the algorithm would directly give better algorithms for our problems. Yeah. So we really show equivalence. So how are the problems connected? Like how can we compute the residue table by using min plus convolution? That is actually not very hard to see. And the idea is simple. We can define some initial sequence. Like we just fill the table with the initial item sizes, A, okay. And if we do not have an item for a residue class, we simply put in infinity values. And then the idea is now we can just apply the min plus convolution iteratively. So every time we find some subadditivity, so two indices that sum up to a smaller index, then we know this is erased in one iteration. Okay, so in the end, we will terminate at a sequence that fulfills the subadditivity property. So there will, of course, be no more indices anymore that are subadditive, and hence the table that we obtain in the end has to be our residue table. Is that clear?
Yeah.
Okay. So the central question is now just how many min plus convolutions do I have to apply? And this is where we actually use results on the structure of solutions. So there was actually quite some research, more I think in the integer programming community, and what we use is that some sparsity result. Okay, so if the IP is feasible, then there also exists a solution X that is rather sparse. So there might be some components that have very high multiplicity, but most of them will be 0 or have very small multiplicity. So a corollary of that lemma would be that the support, which is the number of non-zero components, is only logarithmic in A0. So there's, for example, also this result by Eisenbrat and Schmonin, which shows similar properties on solutions of feasibility integer programs. So in the sense, we know that there always exists a solution that uses very few different item sizes, although they might have very high multiplicity. So the question is, like, how do we deal with these high multiplicities? But it's good to know that we only use very few different item sizes. Okay, so the idea is we start with a residue table that does not only contain the item sizes, AI, but we fill them by all binary exponents of the item sizes. Okay, and then we apply min plus convolution to this increased residue table. And this is where the structure property comes into play. So now I think we have target value Ti, which is the minimum for our respective residue class. And then we have a solution to the Ti. So Ti can be represented by this solution. And we're having the property that the sum of the logs is less equal to the log of A0. So this is just applying the logarithm to both sides of the inequality. So this is why we have this property here. And then we can encode the multiplicities by the binary exponents here in the sum. Okay, so each element here appears in our variables that we have started with. And so for each sum, we use exactly log xi plus 1 many sums. And this is then in total precisely bounded by log A0. So this is how we prove that we only need to apply log A0 many min plus convolutions to obtain our residue table. And then we can do even better by doing a binary exponentiation argument. So of course we can do A plus A, and then to obtain A prime, and then we do A prime plus A prime to obtain A2 prime, and so on. So the final result is actually we only need to apply log A0 many min plus convolutions to compute our residue table and therefore solve the unbounded subset sum problem and also the Frobenius problem. Because if we have, if we have the residue table, this is a generalization of both of the problems. So let me just take a look at how much time I have left. Oh, okay, I have to hurry up.
Oh, I just had a quick question. So the support bound, is that only for the coefficients that are off of A0? I mean, like, if I understand it correctly, it's just saying if you have this large product, then you can move weight onto A0.
Mm-hmm. Yeah, exactly. Yes, essentially the proof works like this. You push, you use A0 as often as possible. Yeah, exactly. And this is counted.
Yeah.
And yes, a corollary of this is there's a very efficient algorithm solving min plus convolution that is, of course, not subquadratic, but nearly subquadratic, the famous algorithm by Williams. So kind of this gives us the best running time so far to solving the problem. I mean, the algorithm of Bücker and Liptak is more efficient if n is very small. But if the number of items is close to A0, then this algorithm will be more efficient. And yeah, this term is a bit hard to pass, but you can just think about it grows faster than any polylogarithmic function. So it's nearly subquadratic in a sense. Okay, so to give you an overview on what I proved in general is that all problems are really equivalent. So min plus convolution can be solved in subquadratic time if and only if each of the other problems can be solved in subquadratic time. So essentially what I've showed you so far is the direction on how to solve the residue table by using min plus convolution. And these arrows are trivial because they are contained in each other. And what I did not show you is that the subadditivity testing can be solved by using the subset sum problem or the Frobenius problem. And this arrow was already known by the paper of Sügen and others. Okay, but this whole thing gives you the equivalence of all problems. Okay, so let me just tell you what we know for the parameterization by AN. So then we use a bit of a different approach. So yes, so the idea is, maybe I can tell you this, the idea is to define, now I partition the line of numbers into intervals of length AN. So this is kind of now the interval length to keep in mind. And then essentially what we apply is also the sum set computation, which is the FFT approach that Carl was also talking about. And the idea for the algorithm is, I mean, this is similar to what the Janssen and Rohwedder algorithm does, but with a bit of a catch, because we can make use of these feasibility sets in a clever way. So the idea is to only compute the feasibility sets that are powers of 2. And having those feasibility sets, then we can compute any other one. So the feasibility set that we would like to know is the one that contains our target value of interest. Let's call it AK. And we can kind of do that in a binary fashion, binary exponentiation fashion. And the idea of doing it that way is good because now we can also solve the Frobenius problem in near linear time. That was not known before. I think there were no real algorithms that considered the Frobenius problem parameterized by AN. At least I'm not aware of any. And the idea is that the Frobenius number is contained in the largest feasibility set that has not all numbers contained. Okay, so I'm a bit too vague here, I fear. So a feasibility set essentially contains the set of feasible targets. Okay, so and it's clear to see that the cardinality of the feasibility sets increases by its number, right? So once we have reached AN, sorry, that has to be AN, then of course the cardinality has to be equal to all following feasibility sets. And so the Frobenius number has to be contained in the largest that is less than AN. And now we can compute this by a binary search. This is the whole idea. I hope you got it. Maybe I do not go into more details here. So this was the one algorithm. And yes, then there's the lower bound that was already known by the paper of Bringmann and also Janssen and Roverda talking about this. So we know we cannot solve this in sublinear time. You cannot solve the unbounded subset sum problem in sublinear time in AN. And actually this lower bound holds also for the Frobenius problem. So this is what I showed in the paper, that this lower bound can be transferred also to the Frobenius problem. Yeah, and also what I also did is an algorithm with complexity AN of 3/2 for computing the residue table. So all targets is computing the residue table. And I have no idea if that algorithm is actually optimal. So I was working actually very long to improve that algorithm, but this seems to be very tough. But I think it can be improved, but not by some easy trick. I tried long on that problem. So that's maybe an open question to, if you're interested to work on that. So yeah, that's what I wanted to say. How much time? Oh yeah, it's already time over for me. So that's it. Thanks so much for your attention.